So if you turn in your booklet to page 13, we'll make a start there. So this is the second of two reactions that we need to study with alkanes. The first one was combustion, so have another look back at that. And there was some information that we didn't cover in much depth in class on catalytic converters and their role in the reduction of pollution from burning alkanes and their impurities and so on. So have a wee read through that, work through that by yourself, and there's some questions at the back of the booklet that you can answer to help apply your learning with that. But we're going to jump in at this second reaction, the substitution by a halogen. And if you remember, we talked about how alkanes are fairly unreactive. And that's because they have no functional group. So I've drawn two molecules at the bottom of this page, ethane and ethanol. You don't necessarily have to write this in, but it's just to show you that alkanes, so ethane in this example, don't have any functional groups, whereas ethanol does have a functional group, this OH group. So you can see these molecules only differ by one atom. Ethanol has an oxygen atom, but the presence of that OH functional group makes ethanol much more reactive, much more prone to reactions than ethane. So alkanes don't have a functional group, and a functional group is just a reactive group within a molecule where most of the reactions of that molecule occur. And alkanes' lack of functional group makes them very unreactive. But one reaction we can do is this reaction of a substitution by a halogen. And so essentially, in this reaction, we are replacing a hydrogen atom within the alkane with a halogen. So, for example, we could be converting methane into chloromethane by the reaction of methane with chlorine. But as we said, alkanes are very unreactive, and so we need to go through a bit of a process in order to get this to occur. So in order to understand this reaction, we need to introduce a few definitions, ones which you may not have met before and may seem quite complicated initially. This is quite a unique reaction to alkanes that we will study. So we'll meet the term a free radical. So free radicals are just particles which have an unpaired electron, and that makes them extremely reactive. And unstable, essentially. And how we indicate those particles is by the molecule or the atom with a little dot beside it. It's usually in the top right hand corner, and that's not shown very well in the document. So like that, Cl dot in the top right hand corner, or even in the top left hand corner if you're using it in a mechanism. It sometimes makes it easier to represent, but this is generally the way we would show it in an equation. Substitution is another term we'll meet. This is the type of reaction. It's a substitution reaction. And that essentially is where one atom or a group in a molecule is substituted for another. And as we saw on the previous slide, in this reaction, hydrogen atoms are substituted for chlorine atoms, or indeed bromine atoms. That can be studied as well. A photochemical reaction, and this reaction is a photochemical reaction, is one which is caused or initiated by light or ultraviolet radiation. So essentially we need light or UV radiation to get this reaction going. So this is a photo, which literally means light chemical reaction. The next term you need to be familiar with is the term homolytic fission, and that is what happens in this type of reaction. And we'll have a look at this down at the bottom of this page as well to show you that in terms of electrons, what happens. But if you think about a covalent bond is one shared pair of electrons. So homolytic fission is where that covalent bond is broken, and the atoms that share that bond each get one electron. If we look at the word homolytic itself, we can get that definition almost from the word. The little prefix homo means the same, and lytic means is representing the breaking of that bond. So that word homolytic is representing that the covalent bond is breaking in such a way that the atoms each end up the same. In other words, the shared pair of electrons is divided equally. So we'll look at this in a bit more detail at the bottom of the page. But essentially, if we had a chlorine molecule with one shared pair of electrons between our chlorine atoms, each of those atoms would end up with one unpaired electron after the bond breaks. And then just to introduce you to this term, so heterolytic fission does not happen in this type of reaction, but just to compare it to compare homolytic fission with heterolytic fission, that's what we would normally see when a bond breaks. This is what we would be more familiar with. Heterolytic fission is when a covalent bond is broken and the products end up being oppositely charged ions. And that's because in this particular covalent bond and the breaking of that bond, one of the atoms of the bond will end up with both of the shared electrons, so it'll end up with the electron pair, and the other atom will end up with neither of the electrons. So heterolytic fission literally means different breaking of the bond. So in other words, the bond breaks and the products are different. So if we were to look at that in the likes of a molecule of hydrogen chloride, this is a polar bond, a polar molecule, and so therefore chlorine has a greater pull on the shared pair of electrons. It's more electronegative. So when this bond breaks, it does so heterolytically, and so therefore the chlorine atom takes both of the electrons and the hydrogen doesn't get any of them after the bond breaks. And so what we end up with is a positive hydrogen ion and a negative chloride ion. So that's heterolytic fission, when the electron pair goes to one of the atoms and leaving the other atom with none of the electrons. So let's take a closer look at how that happens with these two examples that we've looked at, with chlorine and with hydrogen chloride. So if we start with the homolytic fission of chlorine, so if you start your little diagram down here with a simple dot and cross diagram of a chlorine molecule, and then we'll have a look at what happens. So this sort of splitting of a bond is initiated by light. As we said above, that's a photochemical reaction. And essentially, the light causes this bond to break homolytically. So I like to sort of represent that by a lightning bolt. And you can see how that is splitting the bond homolytically. And what will happen is each of the chlorine atoms is going to break off with one unpaired electron. So what we produce is two chlorine atoms, which you can almost see it's like they have their original electrons back. So each of these atoms will have 7 electrons in their outer shell, but most importantly, which will determine the reactivity of these particular particles, is that they have these unpaired electrons. So each of them has one unpaired electron, and that's what makes them what we call radicals, and that makes them really unstable and really reactive. So these unpaired electrons make the atoms particularly reactive. So homolytic fission of a covalent bond is the equal splitting of that covalent bond, so that each of the atoms that originally shared a pair of electrons each leave with one electron, and that electron is unpaired and makes it really reactive. But let's have a look at heterolytic fission, and we'll use the example of hydrogen chloride. So let's again start with a dot and cross diagram of that molecule. So you can see it's just quite a simple molecule that shares one pair of electrons, one from hydrogen and one from chlorine. But when that bond breaks, what will happen is that the chlorine atom, because it's more electronegative, will escape with both of those electrons from the shared pair. And what we'll end up with is hydrogen with no electrons, and so therefore it's a positive ion. And we'll end up with a chloride ion. So it's escaped with both electrons from the shared pair. And so now it essentially has one extra electron, and therefore it's a negative ion. So this is the way we would normally see a bond breaking. And so this produces oppositely charged ions, and so therefore this is heterolytic fission, because the covalent bond has broken in a different way, in a way that we have produced different ions. You can see in homolytic fission, it broke in a way that both of the particles that were produced were identical. There was an even splitting of the covalent bond, but in heterolytic fission, we see that it breaks in such a way that we're producing different particles, oppositely charged ions. And it's the homolytic fission of bonds that we will see in this particular reaction of our substitution of alkanes with halogens. So now that we've met some of the key definitions for this reaction, let's look at the mechanism. And mechanisms are something that you'll meet right throughout your experience of organic chemistry, both in AS and A2. And mechanisms simply show a step-by-step sequence of reactions, and they show the movement of electrons in a reaction. Movement of electrons is shown by an arrow, and there's two different types of arrow that we use in our mechanisms, and let me show you those now. So the most common type of arrow that you'll meet is what we call a double-headed arrow, what you would probably see as a normal arrow, and it's always a curly arrow, so you can see that it's got a curve in it, and that shows the movement of a pair of electrons. So in other words, the movement of two electrons. That's the one that you'll see in most mechanisms, but it's not actually the one that we'll see in this mechanism. This mechanism of the photochemical substitution of alkanes with a halogen is actually, we're going to see a single-headed arrow, so like this. So you can see that it's essentially like half an arrow. And that represents the movement of a single electron rather than an electron pair. So we'll be meeting both of these types of arrows in our mechanisms that we see in our study of organic chemistry in the next few topics. And you need to be familiar with what they represent, and they always show the direction in which the electrons are moving as well. But as I said, it's this type of arrow that we're going to use in this mechanism. So, as I said, a mechanism is just a step-by-step process of what happens in a reaction. And as we said previously, this reaction proceeds by photochemical substitution, this term here. And that just simply means that it needs light to get it started, and that's due to the lack of reactivity of alkanes. And that light causes the homolytic fission of our halogen molecule. So let's have a look now at what this mechanism looks like. So this first step of the process is called the initiation step. And in this example, we're going to look at the chlorination of methane. So methane is our first alkane in the series, and it has just one carbon, so it has the formula CH4. And essentially we're going to react it with chlorine, and as a result we'll swap one of our hydrogens, or substitute one of our hydrogens with a chlorine atom, and we'll produce chloromethane and a hydrogen chloride. So the first step of this reaction, the initiation step, involves the chlorine molecule undergoing homolytic fission to produce two chlorine atoms, and these atoms will be radicals because they will have an unpaired electron. So in this type of reaction, this stage of the reaction, we've got a molecule breaking down to form two radicals. That's represented by the equation written on page 15 that you can see there, Cl2, and then an arrow with UV written on top to show that light is needed for this process. And we're forming two chlorine radicals. So let's have a look at what that looks like in terms of a mechanism. So let's just draw our chlorine. With our bond between it, it has a single covalent bond between the two chlorine atoms, and we'll show the electrons. We'll show them both with dots because that's how the free radicals are shown, as dots rather than crosses. But I'll show them in two different colours so that you can see that they're going to the different chlorine atoms. And as we said, these mechanisms are represented using single-headed arrows because they are representing the movement of a single electron, not an electron pair. So what happens is this homolytic fission causes one electron to go to one chlorine atom. Okay, and you can see the single-headed arrow that I've used there to show only one electron is moving. And the other electron goes to the other chlorine atom, again represented by a single-headed arrow. So what does that produce? Well, we have a chlorine atom with what we represented with the black dot, that electron. So that's a chlorine atom with an unpaired electron, which makes it a radical. And the other chlorine atom escapes with the green electron. Now, obviously, electrons aren't coloured in real life, but it's just to show the movement of the two different electrons. So essentially what we formed here are two chlorine radicals, which are extremely reactive, and they will then go on and react with our alkane, and we'll see that in the next step. So you may want to write underneath that on the left-hand side we had our molecule of chlorine, and that has now undergone homolytic fission to produce two chlorine radicals. The next step of the reaction is called the propagation step. And that's essentially where we've got a radical reacting with a molecule. And these type of reactions cause a radical to be regenerated. And so therefore this reaction just keeps going as a series of chain reactions. It's why they're quite dangerous, they're quite difficult to control. So the pattern for this step of the reaction is where a molecule reacts with a radical, and that produces a radical and a molecule. What we mean by that is essentially the thing that started as a molecule in this step will become a radical, and the radical will become a molecule. We can see that in our equation below. We can see that a molecule is reacting with a radical, and we're producing a radical and a molecule. So the molecule we start with is methane, and then that reacts with the chlorine radical that we produced in step 1, the initiation step. And then the methane molecule becomes a radical, and the chlorine radical becomes a hydrogen chloride molecule. Let's have a look at what that actually looks like in terms of our mechanism. So first we're going to start off by drawing a methane molecule and draw the structural formula so we'll see all the bonds. So we've got CH4, a carbon surrounded by 4 hydrogen atoms with single bonds. Let's show the electrons in one of the carbon-hydrogen bonds. So we'll do that as a dot and an X. Then let's represent our chlorine radical that we produced in the initiation step as a Cl with a dot in it to show that it's a radical, that it's got an unpaired electron. So what happens with this is essentially we're forming hydrogen chloride, and how that forms is the carbon-hydrogen bond breaks, and one of the electrons is used to form a bond between the hydrogen and chlorine, and the chlorine radical uses its single electron to form that electron pair. And we'll see that in the products, how hydrogen and chlorine are now bonded together with one of the electrons from the original carbon-hydrogen bond and the unpaired electron of our radical. So this carbon-hydrogen bond is breaking, and as a result, this electron moves in towards our carbon atom. So that's just another single-headed arrow. And essentially now you can see that is producing a methyl radical. So what do we end up with? Well, there's our CH3 molecule, but it now has an unpaired electron associated with the carbon atom. And so that is now what we call a methyl radical. You can see that in your equation above. And what else do we get? Well, we get hydrogen that is now bonded to chlorine using the original electron from the chlorine radical and the other electron from the carbon-hydrogen bond. So remember, for a covalent bond, we must have a pair of electrons. So here we're essentially breaking a covalent bond. You don't need to highlight this in your notes, but just as I'm talking through, we've broken this covalent bond, the carbon-hydrogen bond, and that has broken homolytically as well. So where one of the electrons goes into your carbon atom to form a methyl radical, and one of the electrons is used to form a bond with the chlorine radical. And as a result, we form our hydrogen chloride molecule. So it's important that you're able to represent the movement of electrons, and you can understand how the electrons are rearranging to break bonds and form bonds. But the reaction doesn't stop there, because we haven't got our desired product. Remember, what we want to make here is chloromethane. And so what happens is this methyl radical that we formed in part A goes on and reacts with a chlorine molecule to form our chloromethane. So the equation is represented there. Here we've got a methyl radical reacting with a chlorine molecule to form chloromethane, and our chlorine radical is then regenerated and can go on and react with another molecule of methane. So in other words, part A starts again. But let's have a look at this mechanism and then we can have another look at that. So we're starting with our methyl radical that we formed in part A and another chlorine molecule. So what happens here is the methyl radical reacts with the chlorine molecule, and essentially what we want to see is the carbon forming a bond with the chlorine. So it uses its single electron, and this chlorine molecule breaks homolytically again, and that electron is used to form a bond between the carbon and the chlorine. This electron then needs somewhere to go, and it goes to the other chlorine atom within your original chlorine molecule. So what do we produce then? Well, we've got our methyl part, and then we've now formed a bond with one of our chlorine atoms. And then we need to show how that bond has formed. Remember, a covalent bond is a shared pair of electrons, and where that has come from is from the unpaired electron of our methyl radical and one of the electrons of our original chlorine-chlorine bonds. So that little X represents that. What else do we produce? Well, we've got a chlorine radical has now been produced as well, because of the homolytic fission of that chlorine bond, where one of the electrons moved to that chlorine atom. So it now is a chlorine atom with an unpaired electron, making it a radical. So you can see that our chlorine radical, which was used up in part A, has now been regenerated in part B, and it is now ready to react with another methane molecule. And what we've also produced in this step is our desired product, where we have produced chloromethane, that has been produced from methane. And how has that happened? Well, ultimately we've had a substitution where one of the hydrogen atoms in our methane molecule has been substituted for a chlorine atom. And that needed to happen with a chlorine radical, because a methane molecule would have been too unreactive to just react with a chlorine molecule. So you can see part A of the propagation reaction is a methane molecule reacting with a chlorine radical to produce a methyl radical plus a molecule of hydrogen chloride. And then in part B, our methyl radical goes on and reacts with a chlorine molecule to produce our chloromethane, and our chlorine radical is regenerated, ready to react with another molecule of methane. So these reactions can just keep going and keep going, but ultimately we want them to stop at some stage. And that's where part 3 comes into play, which is our termination step. So let's have a look at that now. So the only way to get these reactions to stop is by two radicals reacting together to form a molecule. So if you think about it, if you had two radicals reacting together, then their unpaired electrons would come together and form a covalent bond, and that would lead to a stable molecule. So the products of these termination steps are stable, and they ultimately stop the reaction. When these radicals react together and form molecules, then ultimately there are less free radicals in our reaction mixture, which will eventually react together and terminate the reaction. And actually we'll look at in a second, if this reaction wasn't terminated, then more substitutions can happen. But let's have a look first of all at what options we have for these termination steps, because if you think back to our propagation step, we had two different types of radicals in this reaction. We had our chlorine radical and we also had our methyl radical. So as a result, we have three different combinations of that. We could have two chlorine radicals coming together, two methyl radicals coming together, or one of each coming together. So part A represents two chlorine radicals coming together, and let's just show the mechanism of this so that you can understand what's happening here and why these ultimately then terminate and do not form radicals anymore. So we've got a chlorine radical, which will represent with a black unpaired electron. And then we've got a chlorine radical, which will represent with a green unpaired electron. And essentially, we just use our single-headed arrows to show them coming together and forming a covalent bond. So that green electron with a single-headed arrow, and the black electron with a single-headed curly arrow. And when those come together, they form a covalent bond between our chlorine atoms with a black electron and a green electron. Again, not coloured in real life, but that shows them coming together. And so what we form, you can see the equation written here, is two chlorine radicals reacting together to form a chlorine molecule. And you see there's no radical symbol anymore, because those two unpaired electrons have come together and formed a covalent bond. And so therefore we have a molecule which is a lot less reactive than our chlorine radicals. We can also have two methyl radicals coming together, and that actually produces ethane. Let me show you that in a wee mechanism. So we can draw a methyl radical with a black unpaired electron and a methyl radical with a green unpaired electron, again just to show the movement of the electrons. You wouldn't have to show these as coloured electrons in your exam. So these two electrons come together, single-headed curly arrow from the black electron, single-headed curly arrow from the green electron to show those coming together, forming a covalent bond. So that covalent bond is formed between our two two carbon atoms. And then we've got our original bonds to the hydrogen atoms. And we can see here the molecule that we formed is C2H6, and that is our alkane called ethane. And then finally, our last option is if we had a methyl radical reacting with a chlorine radical. So we'll give our methyl radical a black dot for its electron and the chlorine radical a green dot. Again, using our curly single-headed arrows, we can show the movement of these electrons coming together and forming a covalent bond. So there's our methyl part, now bonded to a chlorine, and we can show that bond with our two electrons that originally came from the radicals. And you can see how that's formed chloromethane, which is our desired product as well. So these termination reactions are simply two radicals coming together and forming a molecule. This is probably the most straightforward step, because just think of the two different types of radicals that you have in this reaction. You have a chlorine radical, a methyl radical, and any combination of those two can come together. And we have to terminate this reaction if we want our product to be just chloromethane. If we don't want these other hydrogen atoms substituting for other chlorine atoms. If the reaction is allowed to continue, then this molecule here, chloromethane, could go on and react with another chlorine radical. And ultimately, if it would be allowed to continue, we could end up with a product called tetrachloromethane. In other words, where all four of the hydrogens had been substituted by chlorines. So these reactions are summarised down below, and you can see the first reaction is the one that we have just shown the steps for producing. So methane reacting with a chlorine molecule to produce chloromethane and a hydrogen chloride molecule, and that went through the different steps where initially this chlorine molecule would have to form chlorine radicals and so on. That is just a summary of the reaction, but you can see from the rest of the reactions then ultimately that our chloromethane could react with another chlorine molecule, and another one of the hydrogens could be substituted by a chlorine atom, and so we'd end up with two chlorine atoms and two hydrogen atoms. Then we could take that and react it with more chlorine, and there would be three chlorine atoms attached to your carbon. Then we would take that trichloromethane and substitute our final hydrogen atom, and it would form tetrachloromethane. So you might want to write the names of those products beside the equations if you wish. And overall, the equation for the tetrasubstitution, in other words, substituting all 4 of the hydrogen atoms with chlorine, is CH4, your methane, reacting with 4 chlorine molecules to give your CCl4, your tetrachloromethane, plus 4 hydrogen chloride molecules. So this is what can happen if termination does not happen. The reaction will continue as a series of chain reactions and continue to substitute that chloromethane molecule. So over on page 18, the final page of your notes, there's an overview of the chlorination of methane. And this is essentially an overview of the steps, but isn't the mechanism, because the mechanism will involve curly arrows that represent the movement of electrons, the breaking of bonds, and the formation of bonds. But if we just have a quick look at this gives you a helpful overview of the chlorination of methane and helps you see the movement of radicals as well. So in the initiation step, we see that radicals are created. So that is involving UV light. That can be shown above the arrow. I know your arrow is not very long there, but that involves UV light, and that involves the homolytic fission of that chlorine-chlorine bond, which we saw in our mechanism. Then once those chlorine radicals are formed, we see our propagation step, which is essentially our series of chain reactions, where in this step, in this stage of the reaction, initially, a methane molecule will react with a chlorine radical, and that's where our radicals are used. So our chlorine radical is used there. That's where we form the methyl radical and a hydrogen chloride molecule. And that methyl radical then goes on and reacts with a chlorine molecule. And you see, as a result, the chlorine radical is regenerated. So in the propagation step, again, we see a radical reacting with a molecule to form a molecule plus a radical. And the radical that we use up in part A of the propagation is then regenerated in part B. And then finally, in our termination step, we see that our radicals are removed. And that's important because otherwise this reaction would just continue going on. So in the termination, we have 2 radicals forming a molecule. So again, in the initiation, we've got a molecule forming radicals. In the propagation, we have a molecule reacting with a radical to produce a radical plus a molecule. In other words, the molecule becomes a radical and the radical becomes a molecule. And in the termination, we have a radical reacting with another radical to produce a stable molecule. So hopefully that all made sense. I know it's quite tricky and it's the first time you've met a mechanism. And in fact, this type of mechanism is quite unique. We'll not see that type of mechanism again. The mechanisms that you'll see from now on will all be using those double-headed arrows because they'll show a movement of a pair of electrons. So hopefully it will be helpful, at least in introducing the ideas of mechanism. And remember, at this stage, you don't need to be learning off these and be able to do these by heart, but hopefully it will make sense and show you that type of reaction. So down at the bottom of page 18, you have a summary of this type of reaction, starting with explaining that because of the lack of reactivity of alkanes, they need a specific set of conditions in a very reactive species called a radical to persuade them to react. And you can read through the rest of that. It's just a summary of the reaction. And just to say then at the bottom, you could also be asked for the bromination of methane, and it's just exactly the same mechanism, but just with bromine. So maybe if you wanted a little bit of practice, it might be worthwhile getting a file page out and seeing, can you redraw that mechanism for the initiation step, the propagation step, and for the termination step, but try it with the bromination of methane instead of the chlorination, and you'll see it's exactly the same mechanism, but it might be good at practicing writing that out for yourself. So even try and study it and then see if you can do it without your notes.